This video is brought to you by FlexiSpot. Hi guys, welcome to Amateur Chemistry. So imagine a chemical that could make solar panels twice as efficient, upgrade and massively cheapen OLED displays, and allow some really impressive electronics to be created. This dream material isn't some holy grail of chemistry and physics locked behind years of research, but this humble red powder called Rubrene. You see, Rubrene is truly a one-of-a-kind chemical, and apart from resembling Cheeto dust, its properties and potential applications are so wild they are kinda hard to wrap your head around. Ever since learning about it, I grew really fascinated with how such a seemingly simple thing, made of the same core elements as gasoline, can do everything from powering glow sticks to making next-gen solar panels. All of this, combined with just how beautiful it looks, made me really want to have some to record videos with. However, it turned out that buying it wasn't really an option. That's because, despite being known for more than a century, Rubrene is the definition of an obscure chemical, since only recently did we start really studying it. All this goes to show that it's freaking expensive, and the only real way of obtaining it for me is making it myself in my small garage lab. The one tiny issue with that, however, is that even the simplest synthesis of Rubrene is like the most difficult organic chemistry project I've considered, easily beating things like cubane. To make Rubrene myself, I will literally have to master a good chunk of practical organic chemistry and overcome a bunch of big problems, oh man, which I know will arise since I actually already tried all this in a real university lab with the help of a professor and failed miserably. As you can see, the scope of this project is really enormous, and I haven't done anything like it before, so buckle up as I show you the 2-year journey of actually getting good at chemistry and slowly losing my sanity one distillation at a time. Now, before I start, I want to tell you that chemistry aside, making this video required a ton of work behind my laptop, and that's the kind of job I don't really like. That's why, for a while now, I've been looking to make it more comfortable and healthier, which basically boils down to getting a better desk. The one I'm using currently is, well, trash, being extremely wobbly and set at a constant height, so you can imagine how relieved I was the day when FlexiSpot reached out to me. They've been kind enough to send me their E7L desk, which fits perfectly in place of my old one, and as far as ergonomic desks go, it's truly one of a kind. First of all, setting it up was a walk in the park and took me only like an hour, with all the parts extremely well made and an easy to follow manual. This desk is rather chunky with an extra large desktop perfect for storing a bunch of stuff on. It's also very versatile, allowing you to easily change its configuration to suit your needs. The hardware on it is also really impressive, with 3 very stable legs complete with electric motors, which coupled with this cool control panel allow you to easily adjust your desk's height and even charge your phone. The desk also has a whopping 330 pound capacity and a height range from 25 to 51 inches, making it very easy to use as a standing desk. Its stability is unlike any desk I've ever seen, and its movement is also extremely smooth and quiet. It's also much better than a regular rectangular desk, since the extra space allows you to do many additional things like watching movies or reading books. Now, you might ask why to buy FlexiSpot when there are alternatives such as Uplift or Fezebo, and that's simply because FlexiSpot is better. Compared to Fezebo, it has a much longer warranty of 15 years and a simpler design, and compared to Uplift, it has the same performance for half the price, meaning it's the best value for your money. If you want to get yourself a FlexiSpot desk, I encourage you to visit their website, and they are having mega sales right now, so don't miss out. For $50 off at checkout, use my code YTE7P50 and leave a note saying amateur chemistry. That would mean a lot and really helps support the channel. Anyway, big thanks to FlexiSpot for sponsoring this video, and now back to making Rubrene. Synthesizing it will make me have to do a bunch of really funky chemistry, since assembling this massive molecular structure is, well, hard. Every reaction I will have to carry out is neatly represented as an arrow in this little graphic here, professionally called a synthesis pathway. These small arrows usually represent a lot of pain a chemist has to go through, and here this is especially true towards the end. Fortunately, before I get to making Rubrene and related abominations, I can start reasonably small with a chemical called styrene. It's going to contribute a lot of the final Rubrene molecule and isn't that hard to make, since basically all I need is some good old styrofoam. Styrofoam is mostly air mixed with a small bit of plastic called polystyrene, which is basically a bunch of styrene molecules stuck together in long chains. Those chains easily fall apart under heat, releasing styrene, which is just perfect for this project since I can make the starting material from literal trash and will be able to relocate my funds to some more pricey parts of the synthesis. To start recycling some styrofoam, I first wanted to remove the air from it since it currently takes up way too much space. This can easily be done using the common solvent acetone, which can dissolve polystyrene, freeing all the Chinese air trapped inside. Since I wanted to end up with a good bit of styrene, I proceeded to pour a bunch of acetone into a beaker and dissolve a trash bag's worth of styrofoam in it. This left me with a wide, goopy mess, and to make it into pure polystyrene, I poured everything into a baking tray and let it dry for a week. This made the polystyrene become a solid brick, and to proceed I had to break it up a little. This was easier said than done, and the only thing that really worked was this extra chunky trip runner. With a bunch of these bite-sized plastic nuggets ready, I could now freely load them into a flask, which I then assembled into a distillation apparatus. It will allow me to heat the plastic without air so that it won't burn and collect the resulting styrene vapors. To start it up, I turned on the heating, and it didn't take long for the plastic to start melting and producing tons of this white fog, which condensed and dripped into the receiving flask. At first, this was some residual acetone, but as the plastic heated up, more and more styrene started coming over. This went on for a few hours, with the plastic eventually turning into this bubbling tar, and when the styrene production came to a halt, I turned off the heating and took apart the setup. Along with a bunch of dirty styrene, I was left with an ungodly amount of black tar, which I was luckily able to pour off before it solidified in the flask, and it made for this weird black mirror. Anyway, to purify my styrene, I assembled it into a distillation apparatus, this time featuring a thermometer head, which should tell me which liquid I am collecting based on its boiling point. After a while of heating, something started coming over at 50 degrees Celsius, and this had to be acetone. Then the vapor's temperature quickly rose, and when it hit roughly 145 degrees Celsius, I switched the receiving flask and started collecting my precious styrene. When the temperature started to rise again, I stopped the distillation and recovered my product, which was this beautiful refractive liquid. I managed to make 85.3 grams of it, which is quite a lot and almost exactly how much I wanted. Overall, this step went quite well without any accidents, which is really nice, and now, with my trash-derived starting material ready, I can move forward with the synthesis. The next step is turning styrene's double bond into a triple bond, resulting in something called phenylacetylene, and this is where things start getting tricky. You see, I can't just tell styrene to magically acquire another bond and have to use precisely the right kind of chemical energy to make this transformation happen. Here, that energy is going to come from bromine, which is this cool toxic red liquid, and unlike the university I previously did this in, where they had literal bottles of this stuff, I had to make it myself. Fortunately, around a year ago, I whipped up a kilo of bromine for situations like these, and to brominate my styrene, I first got it all into a flask. I then diluted it with 80 milliliters of the solvent dichloromethane, or DCM for short, and assembled the flask into this ice-cooled addition apparatus supported by my official lab brick, and it's basically a fancy and controlled way of dumping one reagent into the other. Speaking of the other reagent, I weighed out 135 grams of my homemade bromine, which is a small excess, and diluted it down with 80 milliliters of DCM. I then got it into the addition funnel and started slowly dripping this fuming blood into the styrene solution. Upon contact, bromine instantly lost its color, meaning that it reacted, adding itself onto the double bond of styrene, producing dibromostyrene, which dissolved in the DCM. When I added most of the bromine, its color stopped fading, indicating that the reaction is done. To proceed, I assembled everything into a distillation apparatus, and this is to get rid of the DCM since I no longer need it. When all of it was gone, I stopped the distillation and recovered my product, which was this dense yellow oil that quickly crystallized upon cooling, forming a thick slab. I didn't weigh or purify it since I will use it right away to make phenylacetylene, and in terms of yield it should be nearly 100%. This was another one of these reactions that just work, and I was really happy to see that so far this project was going well. I really hoped that this was going to continue, but since now it's time to venture into the realm of triple bonds and cook up some phenylacetylene, I wasn't so sure. Nonetheless, I pushed ahead and added 200 grams of something called potassium hydroxide into my dibromostyrene flask. I then set everything up for a reflux, which basically means that I can now condense any vapors this mixture is going to let off. Now, for anything to happen, I need to have some solvent present, since two solids can't really react with each other. I used some ethanol, which technically makes this concoction the world's worst alcoholic beverage. Anyway, speaking of the reaction going on here, it's called an elimination, and the potassium hydroxide serves to rip the bromines off the dibromostyrene. This may seem a bit pointless since I just put them there, but what makes this reaction special is that the potassium hydroxide also picks up two hydrogens, which results in the formation of the legendary triple bond. A bunch of heat is also generated, which I wasn't really aware of, resulting in this thing nearly exploding on me. Luckily, the reflux and some tactical cold towels managed to calm everything down, and to avoid this happening again, I quickly changed the flask for a bigger one. Then, to force the reaction to finish, I gently heated the flask in a water bath for 2 hours, and now it was time to recover my phenylacetylene from this starry mess. To do that, I first got a bunch of distilled water into the flask, which dissolved some of the solid byproducts and made the phenylacetylene form a separate layer. I used my gigantic separatory funnel to drain off the lower water layer, leaving me with this pitch black liquid containing my product. I dissolved all the remaining junk from the flask in water and washed the phenylacetylene with the resulting solution, which should pull out more ethanol from it. I then wanted to wash my product with some clean water for that extra purity, which resulted in every chemist's worst nightmare, or in other words, an emulsion. You see, when phenylacetylene is mixed with other solvents like ethanol, it can kind of dissolve in water, forming this milky suspension which will never settle out on its own. I was really scared that this forbidden milk would be the end of this project, but luckily, upon adding some salt water and shaking the hell out of the funnel, the layers appeared again. I quickly drained off the water one, as well as the dirty phenylacetylene, and moved on to recovering some more product from all the dirty water this step generated. I basically washed it all a few times with some DCM, in the meantime getting really sick of phenylacetylene's disgusting, burning plastic-like smell. I then washed all my combined phenylacetylene extracts with some salt water to initially dry them and got the resulting liquid into a beaker. To get rid of all the residual water, I used some anhydrous sodium sulfate, and to extract phenylacetylene from this forbidden Coca-Cola, I set it up for fractional distillation. This is basically distillation on steroids, featuring a fractionating column that cleanly separates the vapor's components by boiling and condensing them hundreds of times across its chunky surface area. At first, I didn't really need it since I was just boiling off the ethanol and DCM, but when there was pretty much only phenylacetylene left in the boiling flask, it was time to use some special tricks to make it come over. You see, phenylacetylene normally boils at a whopping 143 degrees Celsius, and that's really devastating to its triple bond, which at these temperatures likes to turn into tar. That's why, to distill phenylacetylene, apart from the fractionating column, I need my trusty vacuum pump, which significantly reduces its boiling point by lowering the air pressure inside the apparatus. It made the phenylacetylene come over at just 78 degrees Celsius, which was very nice, and it didn't take long for all my precious product to end up in the receiving flask. There turned out to be quite a bit of it. It also looked nice and clear, however, considering how dirty it was before the distillation and me not wanting to do chemistry based on vibes, I decided to redistill it for that extra purity. This was really boring, but otherwise went nicely, and after just 4 hours I had some extra pure phenylacetylene along with some yellow gang in the boiling flask, which told me that doing all this was worth it. Anyway, the final yield of phenylacetylene turned out to be 44.5 grams, corresponding to a 53% yield from the starting styrene, which is absolute trash, but considering all the work required to carry this step out, I was happy I got any yield at all. I stored my product in this glass bottle over some magical clay beads, aka 3A molecular sieves, which will make sure the phenylacetylene is bone dry for the next reaction. It will be by far the hardest and most unforgiving step of this whole synthesis, and it's the one that the prof and I just couldn't crack. It's called a Grignard reaction, and is pretty much the only way I can get this gigantic molecular abomination required to make Rubrene. The reaction is basically a whole chemical orchestra and a nightmare for many chemistry students, mostly because it's a real pain to do correctly. You see, if any amount of water gets into a Grignard reaction, be it moisture from the air or the tear of a depressed chemist, the whole thing often just stops working and can sometimes explode. It also requires a whole squad of reagents, and for my one, apart from the phenylacetylene, I need some iodine, extra pure magnesium powder, ammonium chloride, benzophenone, ethyl bromide, and a solvent called tetrahydrofuran, or THF for short. I have all the required chemicals apart from the last two, and when it comes to the ethyl bromide, I just made it myself without much trouble, but the THF is where things get interesting. Generally, the only solvents used for Grignard reactions are THF and diethyl ether, and they both have their pros and cons. Diethyl ether is cheap but extremely flammable and volatile, whereas THF is less volatile and better chemically suited for Grignard reactions, but more expensive, prone to turning into an explosive when touching air, and it also smells like piss. Since in my mind THF is what real men use for their Grignard reactions, it's the solvent I decided to go with, and after doing so much work on this project, I didn't mind spending a few extra bucks and 2 more days in the lab purifying the hell out of my solvent. After what felt like an eternity, I finally had all my eternal life potion ingredients ready, and to finish preparing for the reaction, I used like 2 liters of acetone to thoroughly wash a bunch of glassware and then baked the hell out of it in my oven to ensure it's completely dry. I could then finally assemble this ginormous setup, complete with a pressure equalized dripping funnel sealed with a septum, a condenser fitted with a drying tube, and a DIY argon inlet. Argon is a very unreactive gas, which I will use to prevent air from ruining my reaction, and with everything set up, I could start loading this thing up with reagents. At first, everything went smoothly, and after charging the flask with some THF, magnesium powder and iodine, I now had to slowly drip in a solution of ethyl bromide in THF. This releases a copious amount of heat, and I was aware of that, but what I wasn't aware of is just how bad this old addition funnel was, since even after closing it, some ethyl bromide still passed through. Now, this itself wasn't that bad, but the real disaster struck when I was trying to readjust the funnel and heard this sound. The funnel just gave up and started spilling the very carcinogenic ethyl bromide all over my fume hood and into the flask, which made the reaction mixture uncontrollably boil and made me stand there with an ice bath in my hand, watching hours of preparation go to waste and praying for this thing to not explode. Fortunately, everything calmed down in the end, and after a big time cleanup and a prayer to the soul of Victor Grignard, I was ready to try this thing again. I fortunately could, since out of all the important reagents I wasted just some ethyl bromide, so I assembled this setup once again using a spare funnel with a Teflon valve. This time I was just paranoid about making this whole thing work, and to start this hopefully successful run, I purged the apparatus with argon and started loading in the reagents. I first added 9.8 grams of magnesium powder and followed this up with 100 milliliters of my THF and a tiny speck of iodine. I then sealed the apparatus and started stirring its contents under constant argon flow, during which the iodine should thoroughly clean the magnesium's surface, quote-unquote activating it. I now have to combine this magnesium with my ethyl bromide, and I added a solution of 43.8 grams of it in 10 milliliters of THF to the funnel. I then started very slowly dripping it onto the magnesium, and this results in the formation of something called ethyl magnesium bromide featuring the really cursed magnesium carbon bond. After adding all the ethyl bromide, I should now be left with a really concentrated solution of this stuff, and to put it to use, I have to combine it with my phenylacetylene. For that, I added 41 grams of it into the funnel, along with 40 milliliters of THF, and as you can see, even though I stored the phenylacetylene in a freezer, it went yellow. This wasn't too great, but I honestly didn't care and started slowly dripping it into the flask. In terms of what's going on here, it's honestly just a kind of magic, all enabled by the sheer wrath of the magnesium carbon bond. You see, this bond is really unstable and looks for any reason to completely beat something up. That's why the ethyl magnesium bromide completely obliterates the otherwise really unreactive phenylacetylene, stealing one of its hydrogens and creating this extremely cursed phenyl-ethynyl magnesium bromide species, which is my Grignard reagent. This form of phenylacetylene is similarly angry to ethyl magnesium bromide, and it looks forward to reacting with nearly anything, which in my case will be benzophenone. After adding all the phenylacetylene to the reaction mixture, I heated it for 2 hours to ensure a complete reaction, and then charged the addition funnel with 72.7 grams of benzophenone dissolved in 100 milliliters of THF. I then started adding that into the reaction mixture, and even though you can't really see it, the benzophenone quickly reacts, forming this absolute abomination. This is the actual Grignard reaction, and I know that it might be quite hard to wrap your head around, but think of it as a very precise and tuned chemical energy transfer, which would normally blow up, but with my guidance and a metric freak ton of equipment, it chose to make some funky molecules. Anyway, with all the benzophenone added and nothing exploding, I was really happy, and now all I had to do was just let this thing sit for 2 more hours. This made the solution change color to light brown, and upon cooling it, an off-white precipitate started appearing, which made me just ecstatic.
Hell yeah!
This is the magnesium salt of my target product, and to finish this reaction, I let everything cool down to room temperature and dumped some saturated ammonium chloride solution into the flask. It quickly reacted, creating my final product as a separate layer, and in terms of what this stuff actually is, it's an alcohol called 1,1,3-triphenyl prop 2-in-1-O, which is honestly way too long of a name even for my standards. This is why I will just call it the alcohol as if there were no other alcohol in the world, and before turning it into Rubrene, I need to purify it, since it should be a white solid and right now it's this ugly yellow oil. To start, I poured the entire reaction mixture into my separatory funnel and discarded the water layer. I then used a bunch of anhydrous sodium sulfate to dry the alcohol solution and now had to remove all the THF from it. The best thing to use for this would be a very fancy piece of equipment called a rotovap, and I often imagine just how easy this whole synthesis would be if I had one, but since it's not the university, I had to go the old-fashioned way and basically set my oil up for distillation. Distilling off the majority of THF was quite easy, but when the oil got concentrated enough, the residual THF just didn't want to go away, and I had to resort to basically vacuuming it out, which took forever. After like half a day, I figured that it must all be gone, and to make my product crystallized, I cooled the flask down in an ice bath. This didn't do anything apart from making the oil resemble honey, and it was here that I started worrying about this purification step, since a few online sources explicitly stated that crystallizing this oil was often nearly impossible. I fortunately had one trick up my sleeve, and that was adding hexane as a kind of anti-solvent to force the alcohol out of the tar. At first, this didn't seem to do too much, but then, of course, off camera, a bunch of these beautiful white crystals appeared. I mean, I felt like the chemistry gods gave me a blessing for all the pain I had to put up with, since there was a ton of crystals, and they already looked nice and pure. I vacuum filtered the hexane away, leaving me with this damp powder, which I decided to recrystallize for that extra purity. I did that by suspending it in hexane and heating the mixture, to which I then added small portions of toluene, in which the alcohol is quite soluble. After a while, everything nicely dissolved, and when I let the resulting solution slowly cool to room temperature, a bunch of these cool, needle-like crystals appeared. I vacuum filtered and washed them with some more hexane, and after letting them dry for a few days, I was left with the world's most fluffy and well-deserved white powder. The yield turned out to be 78.5 grams or 69%, and for this particular reaction, I'd say it's pretty damn good. I mean, I couldn't do this in a real university with some serious help and a rotovac app, so it really felt nice that nearly a month of constant work was beginning to pay off. However, I didn't want to call myself a good chemist just yet, since I now had to turn this white powder into some glowy Cheeto dust. The first problem with that was the lack of a good procedure, and the best one I came across was the one from Vogel's textbook. It seemed pretty straightforward, however, I decided to use only 30 grams of my alcohol for it in case something went wrong, and this turned out to be a really good call, since it just straight up didn't work. Even though I did everything exactly like the textbook called for, including acquiring the stupendously rare and dangerous chemical phenol chloride, all I ended up with was just some red, non-fluorescent tar. I was really disappointed, especially because I literally sacrificed my homemade aspirator vacuum pump for this reaction. What the hell? At this point, I really had no idea what to do next, but the one thing I knew for sure was that I couldn't give up on this project, having spent so much time, mental health and money on it, so I basically locked myself in a room and used all my years of chemistry experience to come up with my own Rubrene synthesis. This is amateur chemistry at its finest, and to start I fitted this 2-neck flask with a funnel and an argon gas adapter. Then I got 10 grams of the alcohol into it and dissolved it in 50 milliliters of ultra pure toluene, after which I started cooling the flask in an ice bath and intensely bubbling argon through the solution to get rid of any dissolved oxygen. When I felt it was ready, I slowly poured in 4.2 grams of phenol chloride dissolved in 15 milliliters of toluene. I used a tiny excess of the alcohol to ensure that all the phenol chloride reacts, and the chemistry going on here is honestly just as funky as before, with the OH group on the alcohol being replaced with a chlorine, which causes the whole thing to basically become self-aware of its structure and rearrange into a more comfortable one. It features a carbon atom bound only to 2 other carbon atoms, and this cursed configuration is called an alene. To ensure that it has time to form, I let this mixture stir at room temperature for an hour. It slowly changed color to this lovely orange, and to help the reaction proceed, I poured in 3.9 grams of something called triethylamine. It won't react with the alene, but instead remove a bunch of the hydrogen chloride byproduct floating around and trap it as an insoluble salt, which you can see as this thick white smoke. All this should leave me with a clean solution of the chloroalene, and to turn it into Rubrene, I added 0.7 milliliters of something called quinoline, which is like one of the rarest and most expensive reagents I ever bought. The quinoline doesn't react with my chloroalene, but really eases its conversion to Rubrene and is pretty much necessary for this reaction. To allow it to do its thing, I set the flask up for reflux under argon and started lightly heating it. At first, nothing happened, but after around an hour the mixture turned reddish around the edges, and this indicated that Rubrene was being formed. I was just dancing behind my camera when I saw this, and felt really proud that I actually pulled this off. Yes, hell yeah. The reactions going on here are weird to say the least, with 2 molecules of the chloroalene reacting with each other through a myriad of intermediates to form Rubrene. This reaction proceeds in astonishingly low yield because of the many potential byproducts, but nonetheless it does form a fair bit of Rubrene, and I always wondered how someone stumbled upon it 100 years ago. Anyway, as I continued heating the solution, the red color got more and more intense, and after like 6 hours the reaction was done. To get my product out of the solution, I first passed everything through a vacuum filter to remove all the insoluble triethylamine salt. I then started heating this forbidden juice to drive off most of the solvent and concentrate the Rubrene, and then, after cooling the resulting red tar in a freezer, actually got some of the Rubrene to crystallize. Now, this was huge, since Rubrene is supposed to be extraordinarily hard to crystallize, and after draining the waste solution of my crystals, I could finally behold some homemade Rubrene. This was a feeling quite hard to describe, since after so many weeks of work and literally dreaming about this moment, I achieved it. Now, my Rubrene should be pretty pure since it's crystalline, and in terms of yield, it's trash as expected, being around 1 gram or 9%. I don't really care, however, since a tiny bit of this stuff goes a long way, and I still have like 30 grams of the alcohol. I ran the reaction again on the same scale as before, however this time I just couldn't get the Rubrene to crystallize, always ending up with some intensely red tar. Even though I spent 2 days dissolving, concentrating and trying to crystallize it again, all I got was this tiny bit of Rubrene powder. It nearly doubled my total yield, which was nice, but after all this I wasn't really feeling like processing the rest of the alcohol, so I just got it all into a jar for future me to deal with. Anyway, now that I have some actual Rubrene in these cute little vials, I can finally show you what it's all about, since it's way more interesting than being your average red powder. First of all, it has this beautiful orange-yellow fluorescence, which is some of the brightest and most intense I've ever seen. If Rubrene is dissolved in something under UV light, it makes these glorious streaks of light and is also incredibly potent, with a few milligrams being enough to intensely color a ton of liquid. This intense fluorescence is the basis for many uses of Rubrene, for example, making it a prime contender for a glow stick dye, where it can emit really bright light using just the energy of chemical reactions. I also tried out how it glows in a bunch of different solvents, which turned out just insanely pretty, with each solution having a slightly different shade. This doesn't mean that Rubrene is solvatochromic though, meaning it changes color in different solvents, and this shade difference just depends on how well Rubrene dissolves in each solvent. Moving on, Rubrene also has some very unusual chemical properties, and even though its structure might suggest that it's very unreactive, things like nitric acid can easily oxidize it, resulting in this weird derivative, which displays some nice green fluorescence. Rubrene is just generally prone to oxidation, even by oxygen in the air, which is why it's best stored in the dark and cold, and to show just how fast this oxidation can be, I assembled this little setup with a Rubrene solution being constantly blasted with a ton of UV. Even though completely bleaching it took some time, allowing me to cook an egg on the incredibly hot UV lamp, the solution eventually turned colorless. It should now contain this Rubrene peroxide, and unlike with the nitric acid oxidation, this peroxide formation is reversible, and when I heat the hell out of the colorless solution, it turns orange again. What's quite weird about Rubrene is that even though it can slowly react with oxygen from the air, it's pretty much non-flammable and has a stupendously high melting point of 315 degrees Celsius. At these temperatures, it also starts to sublime and turn from a red solid straight into a pinkish gas. This is officially the world's most expensive way to get some colored smoke, and it also allows chemists to prepare big single crystals of Rubrene to use in the electronics industry. A part of why Rubrene is such an unusual molecule is that consisting only of carbon and hydrogen, it has some incredibly unique electronic properties, being a very good semiconductor, and this allows it to be used in making extremely bright OLED displays, some funky transistors, and in the future solar panels on steroids. I unfortunately won't be exploring these applications of Rubrene in this video, since it's already stupendously long, and instead decided to do something I have great confidence has never been done before in the history of our universe: Rubrene on beans. I bet that I could display this in some modern history museum, and I honestly always wanted to do this if I made Rubrene. Now, this whole journey has been nothing short of wild, taking me nearly 2 years in total, countless hours of work and a bunch of money, and looking back at it all, I think it was quite amazing, and to say that I learned a lot would be an understatement. I hope that this video will serve as a great example that you can achieve literally anything if you just put in the work, and even as an amateur chemist you can synthesize almost any molecule. In terms of what happens next, I have a ton of really cool projects planned, so stay tuned, and for now I have to sincerely thank you all for watching, since this video just wouldn't be possible without you guys. I hope you all enjoyed this project, and if you'd like to support all the crazy stuff I do, please consider subscribing, liking the video and sharing it with a friend if you want to directly contribute to improving my content, as well as have access to a lot of ad-free exclusive videos like my lab tour. I invite you to become a patron. My patrons provide a ton of motivation for me to keep coming up and recording all these projects, as well as most of the funds to keep the channel going, and I want to dearly thank each and every one of them for their generous support. Anyway, again big thanks for watching, and see you all in the next video.